long time coming. Where's Mr. Pick here? Way at the back of the room. Jeff and I were at TACO. We started working on this program 20 years ago. And we've added to it and added to it. We have an upgrade that we're going to start working on here. 7.0 is going to add some additional features on it. Anyway, we're delighted that we finally were recognized after all these years. So this is a program that will compare the operating and life cycle costs of any HVAC system you can dream up. Okay, has anybody here used other software like Train Trace, Carrier Hap? All right, so we got a lot of folks there, right? It's good software, comprehensive, but it's time consuming. It will take you, upwards of 2, 3, sometimes 4 days to model 4 or 5 different systems in a building, right? I want to pick on this gentleman right here. So how long would it take you to do a typical analysis in a building?
Probably about a week.
A week, okay. How would you like to do it in an hour? But send the customer a bill for a week.
I like that.
Yeah, that's what you want to do. Okay. So what we did here is we developed some software that you can very quickly compare up to 4 different systems. Energy and operating costs and life cycle cost. You get to pick all the parameters that go into it. So in other software like Train Trace or Carrier Hap, you might have 20 or 30 screens to go through in order to model that particular system, right? Okay, we're going to do it all from one screen. There's going to be some drop-down menus that represent the screens that you would see in the other software, but you get to do it from one screen. You get to pick anything you want in the building. Believe it or not, it's accurate. We're going to show you one that we just did at AGO on a project in New York City.
Oh, yeah. I was
At least
just there a week ago Saturday.
Yeah, you were just there with those folks. How did it come out, Jay? I'm just curious.
We're moving forward.
All right,
I love it.
they believed our numbers. I like that. It's quick, and the best part is, it's free. You can download it from our website, RPA, HIA. We'll show you what that URL is. Or you can go to the TACO website, and it's available on the TACO website. All right, I'm going to try to go through this real quick, so I can show you a demo of the software, and then leave time for some questions. But again, if anybody's got any questions, please jump in right away. So normally, when we're utilizing energy analysis software, it's typically done at the end of the job. I'm talking about design-wise, to comply with codes, right? The difficulty we have is we want to get as much money as possible into our HVAC budget at the beginning of the project. And that's very difficult to do because normally the architects and the general contractors are in there and they're trying to get all the money for themselves. We want to get money for ourselves. So you need to have a tool where you can analyze different systems up front without a whole bunch of effort in order to get yourself in a better position for that budget. One of the things that's occurring in our industry is the move towards decarbonization, electrification, and in particular what are called thermal energy networks. So this is district heating and cooling. Only the district system is a condenser water loop, just running around your neighborhood or the downtown area. And we call those thermal energy networks, or TEN. So what we're trying to do with BEST is we're trying to upgrade BEST to be able to model these kinds of district energy systems. Currently, BEST models buildings only. Any HVAC system you can dream up in a building. So we want to be able to allow you to model district kinds of systems, including thermal energy networks. Unfortunately, right now, the tools that are available to model and actually provide information to building owners and network providers the tools are there, but they're cumbersome, takes some time to do all that. And so we'd like to speed all that up using BEST, which is a very fast tool. It's what we'll call an early stage planning tool. We use BEST as an early stage planning tool for buildings. We want to have an early stage planning tool for thermal energy networks. That's what we're trying to do here. That's our next step with this software. And it would look something like this on the left here. As you can see here in blue and red, that's hydronic piping. That's a heating cooling system utilizing 2 single pipes. And with a thermal energy network, we use just 1 pipe running around your neighborhood. We can also do the same thing in a building. What's hard to see is that's overlaid on top of a PDF of a building plan. So what we want to be able to do is have you draw the district energy, the thermal energy network, and overlay it on a PDF of the city or your neighborhood, so that you can visually then use that as a tool to present to your customers. That's what we're trying to do here. So currently BEST, again, we only use 5 input screens as compared to 20 or 30 from the other calculations. We utilize the 8760 NOAA weather data. We have about 1,000 locations in North America, between Canada, the US, and Mexico. We reduced that 8760 to bin data, 5-degree bins to speed up the calculations. When you're doing a thermal energy network, you want to share the energy between buildings, and so you generally want to do an actual hourly 8760 so you can see how you can move energy from one building to another. As an example, you might have commercial and residential mix. The commercial buildings are going to have heat gain throughout most of the year, whereas the residential are going to need some heat. They have heat loss, and you want to be able to move that excess energy from the commercial over to the residential sector. So you want to be able to look at that at true 8760. So we need to convert BEST from the bins to the true 8760. Another thing that's occurring, anybody familiar with wastewater energy transfer? Shark, anybody familiar with Shark? So we're going to take the sewer going out of your building, which is about room temperature, and we're going to recover heat from that and use that to preheat the domestic water coming in. So that's new technology. Shark actually has a booth here if you want to go over and look at it. And then what we want to do with BEST, instead of just doing individual buildings, we want to do a group of buildings that you can assemble into some kind of district network or a thermal energy network. Okay, does that all make sense? Questions on what we're trying to do here? All right, well, that's good. Okay, so this is what a thermal energy network can look like in terms of some of the hardware. Here is this single pipe loop running around your neighborhood, and then you have 2 takeoffs, one's a supply and one a return. So we run the water, condenser water, into the building through a heat pump and then dump it back into the single pipe. And then it continues around the neighborhood. They can either add heat to or remove heat from the next building. So there's an example of what that might look like. Here's another one. Again, here's the single pipe connection right there to the building, in and out. Here's an example of a network that might run around a building. Okay. In this particular example, we can have mixed use. We can have offices, retails, and housing all on the same loop and move the heat energy around that loop wherever it's needed. This is what a single pipe looks like. Anybody familiar with single pipe systems? A few. Okay, well, single pipe systems have only been around since 1950. How many years is that? 70? 70 some years. It was actually developed by Bell and Gossett back in the 1950s. It was a heating only system. ACO took that and added cooling to that. They called it load match. There's several other trade names for that. Shear flow, on demand. But it's basically a single pipe loop that's running around your building here, right? In this case, it's cooling. So we have a chiller, just like you normally would. We're running chilled water around. And then each one of these terminal units takes the heat from the space and dumps it into the single pipe loop and runs it back to the chiller and cools it back down. Pretty slick. We're gonna save you a whole bunch of pipe. This is primary, secondary pumping. This is a decoupled secondary loop right there. It's 2 T's, TACO calls it a twin T. You run that water, chill water up into the fan coil and back into the single pipe. Anybody see a difficulty with that? Huh? What's the difficulty?
The quality of the water will degrade.
Yeah. So we call this the temperature cascade. So if you start out with 45-degree water here to 55, that's a normal 10-degree delta T. The water coming into the last unit is 55 degrees, and so you have to pay attention to that and size that unit for the 55 degrees coming in. If you do that, everything is happy. I cheat. I'm lazy. What we have discovered, if you got 45 to 55, there's diversity in the system. And if you size everybody for the halfway point, 50 degrees, it always works. We've been doing this for 25 years. It works just great. We've got systems literally all over the world. The biggest advantage to this is it's self-balancing. The only balance valves occur if you had a riser, but there's no balance valves in the individual terminal units. So we can save you lots of time and effort. There's no control valves. As a result, that's about 20, 25 feet ahead. You're going to see a reduced pumping horsepower here just because we eliminate the heads of the balance and the control valves. Very simple system to install. Can't get any simpler than this. So we're going to apply this now. Instead of terminal units, these are buildings in your neighborhood, right? Instead of a chiller, we're going to use a heat pump. Okay? So that's the only difference. So here's a project that we looked at Egg here some time ago, Penn South in New York City. There are, let's see, 20, 22-story buildings, I believe. 15, 22-story buildings. The biggest one is this guy right here. I got a better drawing of it. Here's the actual thermal energy network running around. The green ones are the multi-story buildings. And then right across the street is a post office. And that post office, back up here, the post office produces 12 MBH of heat all year long, and we can dump that back into the residential buildings. About a fourth of the total heat gain or heat loss we can get from this guy across the street over here. There's a couple purple ones. Those are churches. So again, you got a mixed use here of retail and residential. So here's a tool that we've been using for quite some time. It's called Hydronic System Solution. Anybody familiar with that? HS2. Aha. Mr. Jeff back there. This tool's been around about the same amount of time, 20 years. What it does is it creates a flow diagram for you. Here's the loop running around the neighborhood, and then here are all the individual buildings that are connected up to this. This is actually smart software, it's CAD, so we can actually input the loads into each building, and then that heat is moved downstream and it can be utilized in any other building. Here is wastewater energy transfer. So this is telling you how much load we have for the domestic water heating. And here's a little flow diagram of a wastewater energy transfer system within a building. So this is the total flow diagram right here for the system. So what we're talking about doing is then importing in the background is the actual city map. So this then, you can draw these lines on top of the city map and use that as a presentation tool to your customers. Okay, here's another one. It was a mixed use neighborhood. Here, we use the load diversity just within the buildings, not necessarily trying to calculate how much heat we needed over here because we generated heat over there, but just the natural diversity in the system. If you totaled up the sum of the room or some of the building loads, we had almost 9,000 tons. Just by the diversity, we got down to about 6,500 tons. So again, we're just running heat or condenser water around this neighborhood, and each building can take it or dump heat back into it as it needs it. Okay, here's the Village East Towers. This is the one we're working on right now. This is wastewater energy transfer. The nickname we call it WET, wet. So there's a sewer line leaving the building. That's a big one. 8 inches. And it's about room, the water is about room temperature, around 70, 75 degrees. The water coming in from the city is in the 40s. So we can recover a lot of heat from that wastewater and use that to heat the incoming domestic water. So here's kind of a little schematic of that. Here's the wastewater coming in. This is just a big tank. And here's the wastewater going out. You grind up the solids. We run that into a heat exchanger here. This one is called a Piranha from Shark. It's got the heat exchanger and then an auxiliary heat pump. Whatever temperature we get out of the heat exchange between the wastewater and the incoming cold water, that heat pump will then heat it up to its final temperature, 110 or 120 degrees. So this is a total package system taking heat out of that wastewater and preheating the domestic water as we come in. Here's what it looked like. There were 3 buildings in this complex, 1, 2, 3, and we were proposing to put in the shark unit here. It has to be above ground because that's below ground and we don't have enough space in the lower level to do that, so this would be an above ground type of unit. Okay? So there's an example of another type of thermal energy network that we can utilize. So what we're trying to do here is we're trying to take energy that's available, we'll call it heat recovery, from the cooling system or from the wastewater system and utilize that then to heat the building. So we have this essentially free heat here that we can now utilize from other buildings and other sources. Okay, questions at this point? Comments? Thoughts? We on the right track here? I like that, nodding heads. Okay. So here's a system. This is an all-electric system. We're headed in kind of that direction. One of the difficulties with all-electric systems, if it's a boiler or electric baseboard, is you're going to put a substantial impact on the grid, and we're going to crash the electrical grid. Anybody remember what happened in Texas 3 winters ago? No? All right. What happened there, it got down to 10 degrees in Dallas, and they utilize, for residential, almost all air source heat pumps. And at around 20 degrees, that air source heat pump runs out of poop. It can't heat the building, so it switches over to backup heat, which is strip electric. So everybody is on strip electric and it crashed the grid. Didn't have enough potential. So try to extend that out to the country, and you're going to see what the problem is. So here's a way to get around that if you want to use air-to-water heat pumps. An air-to-water heat pump will raise the temperature of the water to about 100 degrees above ambient. That's the lift. So in cold climates, the best you might do is 100 degrees during the winter. Our problem then is we need to get this up to some other higher temperature. We're going to say 130 degrees to heat the domestic and the space heating. So we run that into a booster, a water-to-water booster, and we connect that up to a higher temperature. At some point, this air-to-water guy, just like an air, is going to run out of poop. We don't have enough heat at the low ambient temperatures. In fact, these guys shut off at around 0 degrees to protect themselves. Think of the oil trying to lubricate the compressor, and we don't change the oil in these guys like we would do in your car. So in the winter, you got a lower weight oil. So what we have to do is protect these guys. They just shut off at around 0 degrees. So below that, we really need this booster here to pump up the temperature. And then when that shuts off, we have a backup boiler. It's okay if that's gas. Doesn't have to be electric. I realize that a lot of people, they want to use electric boilers. Remember, the word here is decarbonized, not uncarbonized. It's still okay to use gas boilers as a backup when this guy's not doing his job. Now, one thing about this system, this is kind of interesting, as we come back to here, and we're going to dump that heat back outside, we could, if we wanted, because we have a booster over here, we could run that chilled water into the booster and use that then to preheat the domestic water. That's pretty slick, huh? All right, so that's an all-electric system, if you want to make this an electric boiler, but in general, if you make that gas, it's still close to an all-electric system. And we can model all this within BEST. I'll show you how to do that. All right, here's a system where we're going to make this a geothermal. Instead of an air-to-water heat pump, this is a geothermal water-to-water heat pump. Here we don't need any backup, because we can get whatever heat we need out of the ground, and we can dump the heat back into the ground. Same thing in the winter or in the summer. We can take that excess heat and run it into here and preheat your domestic water. Pretty simple system. Questions about that? All right, I got to show you this one up here though. This is kind of interesting. So we're going to use single pipe technology. So this is a single pipe here of cold water, and this is a single pipe of hot water. This is an integrated piping system. Anybody familiar with integrated piping systems? 2, 3, all right. An integrated piping system is where you use another piping system in the building to do double duty with the HVAC. Anybody got any thoughts what we can do? Where can we get other water systems in the building? Sprinkler. That was the first integrated piping system back in the 1970s. American Air Filter had a patent on it. We've gone beyond that now. We use domestic water. This is domestic water piping right here. This is domestic water line. We're going to feed cold water to the toilet, and we're going to feed cold water to your fan coil to cool. Heating the same way. We're going to feed hot water to the shower, or we're going to feed hot water to the fan coil. So we're only going to have 2 pipes to heat, cool, and provide domestic water. You're not going to use 6 pipes, 4 for heating and 2 for domestic water. It's the same 2 pipes. So you're going to save, obviously, lots of money there, and we're going to make this much simpler because it's a single pipe, self-balancing. Okay, here's what it looks like. Here's a standard 4-pipe fan coil with 3 pipes for the domestic. This is cold, hot, and recirc, and here's your hot supply and return, cold supply and return. Great system. This is the Cadillac of HVAC systems right here. Great comfort, good energy efficiency. So this is an integrated piping system where we're going to take the mains for domestic hot and cold. We're going to supply the plumbing fixtures, and at the same time we're going to supply the coils and the fan coil. But this is a 4-pipe fan coil, so you got to have return lines, 2 for domestic and the other 2 for return lines. We can do it this way, where we're going to separate traditionally the domestic, we're going to separate the domestic here on their normal 2 lines, and then we're going to make 2 single pipes over here. So that's 4. Ready for this one? How many we got there? 2. We went from that to that. Pretty cool. And BEST can model all this, as well as other things. Okay, here's a water source heat pump. These are water to air heat pumps, standard heat pumps up here. All right, somebody asked me about what was the first integrated piping? Sprinklers. So here it is right here. This is the fire protection line. We're now using for condenser water. It's a single pipe running around the building. So here's your fire sprinkler heads, and at the same time we're running the condenser water into the heat pumps. We come over here. This is a standard boiler tower, water source heat pump, right? If you want to throw in an air-to-water heat pump and make it all electric and not have to use that, at times you can. And here's the heat recovery. We take that water, run it over here into another water-to-water heat pump, a booster, and preheat the domestic water. So there you go, everything right there, utilizing heat pumps instead of fan coils. And here's the same thing, only we're going to substitute now a geothermal system in place of the boiler tower. Yes?
Is that per code for all municipalities across the country? The
Say that again, the what?
Can you use the fire sprinkler line for
Yes,
a condenser source?
yes, it's in FBA 13 paragraph 7.2.
Okay.
Yeah, it's been in there since the 1970s. American Air Filter did a great job with the code people, yeah. I personally went around in the state of Montana in the 1980s and sold this to the fire marshals. You know what the big selling point to the fire marshals is? If you have a regular fire sprinkler system that's stagnant water, right? With oxygen, you're gonna get holes in that pipe. In the early days when you were using Schedule 10 pipes, some of these systems developed pinholes within 3-4 years. We're gonna move the water, and what I didn't show you in here is an air separator. We're gonna take the oxygen out of the air and prolong the life of the pipe. The fire marshals like that a lot. I had no problem getting this approved. And it's been approved for many, many years, and it's in the code. Great question. Okay. All right. Back to best. We're going to call it net the energy. We're going to move the energy around. We're going to recover heat, both from the building and from the wastewater. Okay? Here's what it would look like if you're trying to compare different systems. As an example, over here are fan coil systems. This is a normal fan coil with a boiler and a chiller. Here's a fan coil with the air-to-water heat pump. And here's what a geothermal connection would look like to the fan coil. That's less than half the energy consumption of a typical system. Here's heat pumps. Here's a standard heat pump. Standard heat pump, boiler tower. And here's a geothermal heat pump here. So notice again, what is that? What do you think, Jay? About a third of the total energy consumption there with that system?
About a third.
Yeah, and here's your standard VAV, VRF, and split system. So we're way, way less in terms of energy consumption. Okay, here's how you can download this if you want to. We also have some, I think, John, we still have that up there, the tutorial video.
Yeah.
Right, on the website. So it's just gonna be a repeat of kind of what I'm gonna do here today. I'll show you how to utilize the software. Again, it's free. This, yes,
Is this just for like district heating, cooling optimization, or can you do just one building?
right now it's just one building. The future of BESS is to make it into a district. That's what we want to do,
Okay.
right? Currently, it just models a single building. But it does a great job at modeling a single building. You could kind of model it as a district. I mean, you'd have to make that one building, obviously, the whole district, right? And you could, it models up to 4 systems at a time. So you could make one system the geothermal loop in the thermal energy network if you wanted, as an example. You could do another one, might be an existing system, which is a fan coil or the heat pump or whatever. So you could kind of utilize it as that.
As far as equipment that you're modeling, like say for instance, you have some technology that's kind of newer, but it's a heat pump, would you be able to create the specifications and use your software to do that?
Yes, so what we did was, in here are defaults for everything. Be better if I showed you this. Okay?
Live, right, Greg?
Yeah, let's go live, okay? I apologize here, my computer's got a thing. So what we've done, we have defaults for you for every piece of equipment. So if you have compressorized equipment, we have default COPs for heating and EERs for cooling. You can override those with whatever number you want to put in, right? We don't care. We're just, the thing about the software, we have some wizards to help you get started. That's how you can take 4 days of work and do it in an hour. Because we got all these default wizards. If you don't like our numbers, fine, you'll put in your own number, but in general, we think the defaults are reasonable. What I did was, we took as an example for the compressorized equipment, we took the most efficient at the time we did this, COPs and EERs to put into the default values. So they're pretty decent, I mean, certainly there's been a lot of new technology in the last few years since we upgraded this. Okay? Let's see if I can make this work. My computer's still thinking. Yeah. So to answer your question, yes, you can model whatever you want. If you want to make up your own system, go right ahead. All right. This is as flexible, almost as flexible as train tracer carrier hap in being able to pick all these different values. You can do whatever you want there. The software doesn't care. All right. Everybody see that? Okay, this is the opening screen, get you started. One of the things that we've done here is we have this weather data from NOAA. It's about 1,000 locations around North America, so you can pick that, okay? And we model the building only as a cube. We're not interested in the building, we're just interested in the HVAC system within the building. So to save time and energy and input, we just model this length, width, and then height by the number of floors. Okay? Now, to speed this up for you, we've created some default systems within different kinds of buildings, right? So as an example here, if I did let's just do an office building, okay? And I choose go. Right away, we give you a visual here of what the energy consumption is going to look like in that building for what I consider to be the four most popular systems. See at the bottom here? Okay, number one was a chill beam with a chiller and a boiler. Number two was just a standard water air heat pump boiler tower. System 3 is a VAV system, and system 4 was a VRF. I think those are kind of the standard systems you might see. Again, you can create whatever you want. We just got you going here. Upper left-hand corner, this is the annual energy use. Looks like the chill beams are the lowest, followed by the heat pump. VAV doesn't look too bad, you know. I mean, we've got some people out there that are still selling VAV systems pretty hard, and we can model that. And then here's your refrigerant, the VRF system. Energy-wise, it doesn't stand up at all. For those of you that have studied VRF systems, the actual efficiency, COPs and EERs in operation of a VRF system are about half of the published. And we can document all that for you. Anyway, that's all in the software. Upper right hand, this is the average system life before replacement. That's straight out of the ASHRAE guide. So again, boilers and chillers are going to last a long time. The pressurized equipment doesn't. Lower left-hand corner is the first cost and payback of all that, and then the lower right, again, is the average life. So if I go to advanced, now here's where you can create your own system. These are the system tabs right here. And you can see how you can model different kinds of systems. So right over here, if you go from left to right, the left-hand lower part of the screen are the sources, heating and cooling. The middle are distribution systems, pipe and duct, and on the right-hand side are the terminal units. And then we've added, this is recently, domestic water. You can model domestic water systems in your building, okay? So I want to pick whatever I would like here. So here's a drop-down menu of all the different kinds of heat sources that you can put in this building. Boilers, heat pumps, electric resistance, furnaces, gas-fired furnaces. There's VRF, PTAC units, rooftops. We think all the bases covered. And here's same thing with the cooling units, chillers, condensing units, PTACs, the whole works, right? In this case, it's a boiler, and we said I want natural gas, so you can pick some other kind of fuel for that particular boiler. Here's the piping systems. We got single pipe, we got two pipe. Oh my goodness, we got all sorts of good stuff here for you. And then you can pick how you want to control the pumps. Delta P, Delta T, constant volume, just on, off, whatever. So that's heating and cooling, and then if you got a condenser water loop, would be the same kind of thing here. Here's the air handling systems you can model. I'm kind of proud of this one. Anybody ever heard of a multi-zone system? Ooh, huh?
Oh, yeah.
I grew up designing multi-zone systems.
Not very efficient.
Huh?
They're not very efficient.
No, but that's all we had in those days. That was the technology, right? Dual duct systems, they got a little more, right? Now we're doing single duct. That's great. So you can model all these old systems if you need to and compare. Here's all the terminal units. I mean, we got every kind of terminal unit you could possibly think of here. Air to water, you know, heat pumps, whatever. And again, different kinds of controls for those fans and pumps at the terminal units. And then here's domestic water. So if you want to just model a regular water heater, you can do that, and then you can pick what kind of fuel it is. If you don't like that, if you want to use a heat pump water heater, fine. Here's this water to water, which would be, in this particular case, we could do a geothermal water heater to heat the domestic water. So we think this is a pretty flexible tool here. You can model just about anything you want. So back to, we've created, to help you out, a wizard, Advanced Systems. So if we go to the Advanced System tab here, you can choose a system. All right, let's do that one we were looking at before, which, remember that air-to-water heat pump? We're going to do a fan coil, and we're going to do an air-to-water heat pump with a water-to-water booster. And I like single-pipe systems, and we're even going to do a two-pipe integrated pipe system. Ooh, can't get any more efficient than that one. Let's see, and then we had another one that was a fan coil, right? And we're going to use, I'll have to change this later. We're going to have to make that a heat pump water to water. We'll change that to a, geez, I'm running out of juice here. Holy crap. Hold on here, guys. It says I need to plug in, I think. That's what it says. Maybe we'll plug myself in here real quick like. So can you see how you're picking and choosing all these different components?
Yeah.
If you don't like what we did, you can do whatever you want. Right? We're just trying to get you to us, to the, we're trying to get you to an output quick and easy. All right, any comments, thoughts so far? Anybody like what you see? Remember, this is free software.
That's the best part.
Huh?
Best part.
The best part is it's free. Yeah, absolutely. Uh-huh. We did that deliberately years ago. We want you to design hydronic systems. We don't want to put any roadblocks in your way here. Okay, let's go down now. We'll do a heat pump system. Let's just do a heat pump. We'll use a standard boiler tower, right? Water source to air. We'll do a single pipe there, and this is just going to be a standard boiler tower kind of system, all right? And then finally, we'll do that heat pump system with the geothermal. Okay. We'll do water source to air, and we'll make that a water to water guy, okay? All right, now I choose go. Now I go over here, and most of this information has been filled in for me. Again, I can change it to whatever I want. Here's my air to water heat pump with the booster and a boiler backup. Here's the heat pump, air to water. For cooling, we don't need any backup. Here are the different piping systems. Heating and cooling piping. There's a ventilation system. We're just going to use a DOAS. Fan coil over here for the heating and cooling units. All right. Here's the same system, only what we want to do here is we want to utilize an air to water or a water to air, but we want to make this now a geothermal. We're going to come down here, we're going to make that a water to air, and we're going to make that a geothermal system. So here now I've modeled the same fan coil system, only I'm going to use a geothermal system instead of utilizing the air to water heat pump. Excuse me. Let's see here. This is heat pump, water to air. Well, let's go back to this one. Yeah, this is actually a fan coil system with geothermal. So here's a standard boiler tower with a air-cooled or with a cooling tower on it for the cooling, single duct, all right? And then this one will be heat pump water to air, water loop, only we'll do geothermal, and we'll do geothermal here. So there we go. Those are the 4 systems. Those are the energy costs. Notice which ones are the lowest. Geothermal, right? So this, on the left are the 2 fan coil systems. The one on the left is an air-to-water heat pump with a booster. There's a geothermal. This is a water-to-air heat pump. Instead of air-to-water, it's water-to-air with a boiler backup. That's in the red. And then this guy right here is just the same water-to-air, only we're utilizing a geothermal as the source for the input and output. Okay? That was quick.
Yeah.
Was that an hour?
Not even.
Not even an hour, we did 4 systems. And send your customer the bill for 4 days. Okay? Yes, sir.
You're assuming just a cube for the whole building. How much do you think that will impact the
I'm
detail?
sorry, I'm hard of hearing. You gotta speak up.
Now, you're assuming just a cube for the building, right?
That's correct.
How much do you think that will impact?
Oh, that's a great question. How much will that impact? Just modeling it as a cube. Let's see here. I'm gonna go back. I skipped one of these slides just because I was trying to speed this up. Okay? I should have showed you this one, I apologize. Okay. This is the job we're doing in New York City at Village East Towers. And we're doing a wastewater energy transfer system, WET, right? So we took the actual utility bills from the building and we modeled the HVAC system in the best software. And we compared those. Okay, so let's see here. We got the utility bills are the green, right? If I get the right color, and the blue is the modeling from BEST.
Yep. So it says.
So this is modeling the building as a cube within BEST compared to the real building, which was 3 buildings, 21, 24, and what were they, 10 stories? Yeah.
3 different sizes.
That's almost too big. I mean, I'm kind of embarrassed to even show it to you, because it looks like we cheated. We didn't. I just, we've seen this a couple other times on other buildings where it's really close like this. So we're just utilizing standard calculations. I don't know what to tell you here. The domestic water is the hardest one. See here, in the summer, that's domestic water consumption, right? And we took those numbers right out of the ASHRAE guide. For apartment buildings, so many gallons per day per person. We knew what the incoming water temperature was. So we knew what we had to heat it to because we knew the storage temperature of the domestic water building. And then we modeled this. Gosh, help me, Jay, I forget what the systems were. It was PTAX for cooling and baseboard for heating.
Yes, that's exactly.
Right, the steam baseboard for heating, fired with gas-fired boilers, and then the cooling was just PTAX. This is just the heating consumption. Right? Because what we're concerned with is this domestic water, because that's what we're going to try to do in terms of the heat recovery. So, does that answer your question?
So is this only for existing buildings usually, or new construction as well?
I'm sorry, say that again?
Is this for existing buildings only, or new construction as well?
No, okay, this is, a really good question. So, BEST is for new buildings. Occasionally we do this, where we compare existing energy consumption, because we want to model something with the existing system. So we took BEST and we modeled the systems that we knew existed in the building, right? So now we think we got a pretty good energy model in BEST of the existing building, and then we can come back and say, okay, if we do wastewater energy recovery or whatever, one of the things we're talking about doing, Jay, was putting a geothermal system in the HVAC system. We're going to convert the PTAX and the baseboard to some kind of geothermal system with heat pumps.
Right.
Right? but we've got the energy model now here, so we can do that quickly. But to answer your question, generally best is for new buildings.
What's there?
Yes, sir.
So I know like train system analyzer, you know, you can compare the existing system to what you want to do.
Yes. Uh-huh.
So in your scenario, if you're looking at existing building, so you have to have the energy bills for like a year
Yes, right.
to input.
Well, I mean, you don't have to. I mean, you could take the best model and model whatever's in the building and say it's close, it's good enough, right? In this particular case, we were required by NYSERDA, New York State Energy Research and Development Administration, because they're the ones funding all this. We actually had to produce these numbers to show that our model was reasonable, right?
Now, real quick, Greg, I honestly don't know the answer to this. So you had our engineers model it in BEST first, and then they
Yes.
audited the energy bills and overlaid it.
And overlaid it, they're two different,
Wow,
yeah.
I didn't even
Yeah.
realize that, so.
Yes. So, yes, that's what we did.
Okay.
There's two different, so the best model we did independently. And then we took the utility bills and put the two graphs together,
Wow,
right?
that really did come out close.
It's too close, Jay. I'm almost embarrassed to stand here and tell you that it's that good. But that's what it came out to. So, to answer your question, we think the numbers coming out of BEST are reasonable numbers, okay? And again, if you're modeling, say, 4 different systems in a new building, what you're really concerned about is the difference, not the absolute value. So the difference is going to be good, because you're basing everything on the same set of assumptions. It's a cubic building, here's the weather data, etc., right?
Can you model rooftop units?
Unfortunately. Yeah, I had to stick all that in there. I wasn't, no, seriously, we could model rooftop units. You want a rooftop unit? There you go. We got an even worse one for you, T-tax.
No.
It's all in there, good and bad, because we're trying to give you a tool that you can compare any system, you know, literally in any building, anywhere in North America, quickly and easily. So we've got all of the systems in there, just like I was trying to show you. Here's all the air handling systems. Multi-zones are from the 1970s. Dual ducts are from the 1980s. And then we even did dual duct single fan. Did you ever do one of those? A dual duct single fan? That was a QD. And now we have single duct single fans. They've been around for a long time, so it's all in there. Yeah. All right, other comments here? All right, I gotta show you this one. This is what I think is the most useful part of this software here, okay? This is an estimate tab. So what we do for you, if you use the wizard to select a predefined or pre-configured system, the software will give you the estimated first cost, will give you the maintenance cost, and if you have a replacement life on the equipment, it'll put that in there. Okay, the old train, help me.
System analyzer?
The system analyzer kind of gave you some of that information, right? But you had to input it. This is real data here from real contractors. This was a few years ago. Jeff was with me. Remember that, Jeff?
Yeah, about 20 years ago. I had to bait them all with ski trips in Montana to get them to bring data to us, I remember that. And it worked.
Exactly.
Exactly.
Jeff and I live in Montana. We went to Big Sky, Montana on a ski trip, and we invited, was it about a half dozen? No, what was it, 4 or 5 reps? I kind of forget now, Jeff. It might have been 6 reps.
Roughly half a dozen or so.
We invited reps, the TACO reps, to come in, and then I gave them this form, and I said, here, give these to, you know, half dozen of your contractors in your area, and I put on there all these systems, $1 per square foot, and they sent them back. It was incredible. So these are real numbers, $1 per square foot from real contractors. Now, we have since upgraded that with inflation, because we did that a few years ago. We won't say how many years ago, Jeff.
No, he already did.
Yeah. So those are real numbers. They're not, this is not baloney. It was even, this was kind of cute. One of the contractors actually sent us an Excel file of every job he had ever bid. The name of the system, the price, and then who the competitors were. I mean, it was his business plan. We said, it's never leaving my computer, it's it. Yeah, it was really great information. So, once you do that, right, then I don't have the right numbers in here because we messed around with the systems. But here's a life cycle analysis, and we have the first cost here from that, okay? If you've selected the right system, and these are the paybacks for the different systems over the low price, which in this particular case was a heat pump, boiler tower, right? So it says our geothermal system, this is kind of interesting, has only a 10-year payback. Oh, that's a good one. So anyway, this to me is the most useful part of the software, and then you can get actual life cycle costs to compare different systems. It's not just based on, it is based on energy costs and maintenance costs, but now you can incorporate the first cost here. And again, we don't care what the number is. If you don't like this number, and you want to go talk to a contractor, or you're a contractor and put in your own numbers, go for it. The software allows you to input anything you want to override our default values. The default values are in there to get you going quickly. Okay, what are we doing for time here? About
9 minutes.
9 minutes. Ooh, all right, see? Okay, questions, thoughts? Yes, sir.
Do you model arenas and sports arenas? Is that one of your categories?
Now, we didn't model arenas. Let me go back in here. We did model, let me show you the simple wizard here. Okay, these are all these, right here. So, really isn't an arena in there. But again, this is used to give you the default systems from the wizard. You don't have to use them. That's why I say you can take that and you can go in here to the advanced systems and create whatever system you want using the wizard. If you don't like the defaults, like, I'm back to, let's do a crappy rooftop system here just for grins, okay? So, here's your crappy rooftop system if you want to do that, but if you want to create your own, you go for it. What I typically do is I use the wizard to get me started, and then I know there are some modifications to that, so then I can just go in and click on these drop downs, and I'm, 80% or 90% of the way there. Yeah. Yes, sir.
Can you input your own schedules and set points?
Okay, not scheduled. Let me show you how we do that. So, let me go back to here. So here we're utilizing heat pumps. So this is what I was saying was the defaults for the COPs and the EERs. Those, at the time we did this, were typically the higher efficiency pieces of equipment. So if you don't like that, and you got some new system, and it's got a COP of 8, now you can do that. All right? So it's essentially your schedules, but you have to manually enter that COP and the EER for that particular piece of equipment that you want to model, whatever that is. Okay? So again, you can override anything that we put in here. Okay? As an example here, we have default horsepower. So once we know what the load is, then we can calculate what we think is the horsepower of the pump or the fan for you. Right here. If you got your own design and you want to use your own horsepowers, go for it. Yeah. We're just trying to get you started. Great question. Other questions?
Did you put in the details of the wall to window ratio and all that?
No.
None of with that?
I'll show you how you do that. The software doesn't do it, you have to do it. So up front, I should have explained that. So these are the loads right here, the blue and the red. So we have a default for you here, BTU per square foot. If you want to override that, you can, BTU per square foot. If you've done a real load, then you can enter the breakdown here off of whatever load program you're using right here, okay? And again, it's a block. We're modeling the building as a block. We're not modeling, you know, an L-shaped building or whatever. We don't care about the building. All we care about is your HVAC system. Now, we are going to work on being able to import data from a load tool. It actually can do that right now. Import loads. Mr. Chaffee back here from TACO, many years ago, with Jeff's help, we actually created a load program from TACO called the load tool, and you could import that data directly into this, and that was a real load tool where you could model whatever shape the building was in, and zones and rooms and whatever, okay? That software has since, what do we say, Mark? Just gone out of,
It's no longer supported?
it's no longer supported, right? We'd like to bring that back, so that's one of the things we'd like to do with this upgrade. It's gonna take us some time and effort to do it.
There are lots of load programs out there, so.
Yeah, there's lots of load programs, so you can import whatever data you want, and again, you can import it as a breakdown, or you can just import a total BTU, and it'll, what the software does here, back to the windows, and so we just use some industry standards from the total to break it down into cooling, people, heat gain, light heat gain equipment, BTU kind of square foot stuff. Got another question back here somewhere? Yes, way at the back.
So you might already answered by saying that you're gonna add more load calculations by demoing another like software, but I was just curious if there was like more detail, like you would add in latent and sensible from the equipment as well.
Oh, yeah, that's a good question. All right. So you can input the loads here. So if you want to input the breakdown, now we have the sensible load and we have the latent load. So you can input that. And then when you go to the equipment, wow. Right here are the published EERs from that manufacturer according to AHRI standards. And that AHRI standard has a given percentage of latent capacity that that particular equipment is rated to. So that, I'm going to say here, that EER here is AHRI test standards. And within the AHR test standards, it says you got to provide 15% of your cooling load as latent. Okay? So if you've got somebody else's equipment, then you can utilize that new EER. That help that?
It did, thank you.
Okay. Is there a time here?
Yeah.
One more question, anybody? One more question? Yes, sir.
So is this software mainly for buildings and commercial, not residential?
Oh, it'll do residential buildings, great easy.
Yeah.
Like that was, Mark got on my butt early on and said, hey, we gotta be able to model residential. I said, great. So it'll model residential for you. Yeah. It doesn't care what the size of the building is, doesn't care what's in the building. That's a good question. Hold on here. This is what we did for, over here. All right, here is. We've got it. And pick a boiler, just a second here. If you want a model baseboard, it's in here. Okay? you go, right here. Baseboard fin tube. Residentially, if you want to do radiant heating, there it is.
And follow-up question, how do you input the envelope, the thermal envelope to, in what part of the program do you, like, would look at that?
Right here, okay. It's in the, what we call the project screen, right here. And so here's the thermal envelope, is the BTUs.
Oh, great,
That's the breakdown right there, okay?
okay.
So you can enter it however you want. You want to use our defaults, fine. Defaults aren't that far off, but you can enter your own residence.
Great.
Which is back to the question, again, if you've done your own load calculation from some other program, you can just enter it here, either as a BTU square foot, or you can actually enter the breakdown by the, the walls, ventilation, and it's for cooling, it's people heat gain, light heat gain, okay?
Okay, thanks.
I'm just gonna do a shout out. We work for government agencies. And every time a government agency sees us model the front end with this, they go, how much did this cost you? And can we use it? It's so accurate. It's astonishing, but it's the best kept secret in HVAC, right, Mark?
We try to tell everybody,
It's
spread the
just-
word.
Yeah.
Yeah. Yeah, okay. Am I out of time over here,
You
John?
are out of time. You gotta go accept an award, Greg.
All right. Give us software? We'll do that.
Yeah.
Okay. If anybody wants to come up, we're available here. So thank you very much for spending time.